Hello students, welcome back. We went through a couple of examples on Frobenius method. The first one was the most typical case. This example, when you use Frobenius method, it turns out you have two different R values when plugging n equals to 0, and the difference is non-integer. In that case, you're going to get two different Frobenius series, y1 and y2, and they are linearly independent. Then you're going to get the linear combination as the general solution, ay1 plus by2, like that. Now, if you have just one R value like this, in that case, you got to be lucky. And in this particular case, we were lucky, and we could find two linearly dependent solutions. How about this situation here? Okay, let's work on it. All right, let's keep it as t equal to 0. You see, you can see t equal to 0 is the regular singular point. So Frobenius series is derivative and the second derivative, the usual. And then let's plug those into the original equation here. That's the original equation, but break up the parentheses so that I can actually plug those in. Okay, I just broke up the parentheses. Now, shall we plug in all those series? This Frobenius series to y, and its derivative to this one, and the second derivative to this y double prime. If you do that, you're going to get this. Please check. Did I do this right? Original Frobenius. First derivative. Second derivative. And here I have to put second derivative. Did I do that? Here I have to plug in the first derivative. And did I do this? And these two are the original Frobenius, and this one, and this one. Is everything correct? If everything is correct, then let's multiply this t squared times that so that I get this n plus r power. This second power and minus 2 power cancel each other out. Next, t squared minus 1 power, we get plus 1 power there. First power and that, we have plus 1 power there. And then this n plus r power. So we have all these, and we have uneven powers. N plus r plus 1 or n plus r power. Let's take the same powers, and I can make everything to t to the n plus r power, or everything to the t plus n plus r plus 1 power. Either way, it's fine because 2 versus 2, so it's a push. What did I do here? I think I changed everything to n plus r power. Yeah, indeed I did. So I use index shifting from here to there. Let's see. Let's copy and paste that. And then let's see. Let's look at purple. Did I do this right? I need n minus 1 here, so the total is n minus 1 plus, yeah. So n minus 1, n minus 1, okay, I got it. And then this one. Look at brown and compare. Does it look okay? Again, I change this into n minus 1 here, n minus 1 plus 1 like that. So I need n minus 1 there, n minus 1 there as well. The usual deal. Okay, now look at the entire series here. When n equals to 0, we have only two series, first and last. When n is greater than or equal to 1, we have all four series contributing. So The latter case will give me the general recursion, and the first case, n equals to 0 case, will give me a special R value. Let's see. When n equals to 0, plug in n equals to 0. So from here, plug in n equals to 0, all right. R minus 1, okay, all right. Middle series do not contribute. Last series, just 2 times C0, okay, there you go. Factor C0 out, and I'm getting R equals to -1 or R equals to 2. We have 2 different R values. So looks like I'm gonna get 2 Frobenius series actually of this form, y1 and y2. But there's a bit of a problem. They differ by integers. So the lower series, the lower R value starts, and then that covers the higher thing. So actually, we do not have 2 different series here. So that's going to be a bit of a problem. If we get lucky, we may get 2 different, 2 linearly dependent solutions, or maybe not. We'll see. When n is greater than or equal to 1, all 4 series contribute. So here we go. Plug in appropriate values here, and then solve for Cn. Take the like terms together, simplify and solve. It's a tedious process actually. Elementary but tedious. But in any case, you can solve it. Okay, when R is equal to 2, plug in R equals to 2 there. R equals 2 to this recursion, then we're going to get this expression. And then you can put first several numbers and do some computation. When n equals to 1, we get that. And then n equals to 2, we get this times C1, so and we get that. N equals to 3, we get that. And do we have a pattern? Indeed, we have a pattern, but as a matter of fact, I told you many times already, it's rare. So when you're writing your solution, usually just first 2 or 3 numbers and then dot, 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 and then just move on. Trying to find out any kind of pattern is most of the time just waste of time. But in this particular case, it is possible to find out a pattern. And then we get a Frobenius series. All right? Okay? That's the general term, so we get that. Now, let's do the same thing when R is equal to -1. Okay, plug in R equals to -1 here. And then, let's see, work out. We get something. And all of a sudden, we have a problem. We got 0 in denominator, and looks like this is failing. And this happens when the difference is by integer. You see, n minus certain integer here, that can become 0, and if that happens in denominator, we're in trouble. Consequently, this method fails, and we got only 1 Frobenius series. Ooh, how do we handle that? Well, it is possible to get a second Frobenius series by considering some logarithms and so on and so forth, but I think that's a bit too much, too time consuming, so I'll just stop here. And even though it is possible to progress further, and our textbook does actually a very good job explaining all those things there, but I'm not going to do that. I'll simply say it may be possible, but in many other times it may not even possible, but I'll just stop here. In some case, we may have some situation like this. By the way, if I write an exam problem, the chance is it's not going to be a problem like this. The chance is you're going to get problem like A. You have 2 R values that differ by non-integer. Or in some really strange case, I may give you R value turning out to be a pair of complex numbers, in which case we have just complex power, and that's about it actually. You don't really have to worry too much about changing the complex power into exponential and sine and cosine in my class. It's okay. And just put first several terms of those Frobenius series by recursion and put ... and that's about it. You can just move on. And that is the Frobenius method for regular singular points. And that's where I'm going to stop.